So HNO3, this is your AB, plus CD. But what are we going to use for CD?
And so how do you want to approach this? Do you want to just try a whole bunch of different CDs? Let's say sodium chloride, potassium chloride, lithium chloride, and go on. Maybe sodium bromide, potassium. If you do CDs individually, how many of those CDs do you have to plug in here? That's like doing it one by one. Do you want to do something like this one by one? No, and so the double replacement pattern's wonderful if you're given something that fits the double replacement pattern. But if you're given something that doesn't fit the double replacement pattern, then it's a tremendous amount of work. And so what we have to do is we have to do something more general than the double replacement pattern, and the more general is metathesis. Metathesis is just favorable ion combinations. And so how do we learn what are favorable ion combinations? We learn what favorable ion combinations are just from the driving force for double replacement reactions. When we do this swap, we end up with, we just switch the anions or switch the cations, so we end up with AD plus CB. And then we see, this combination versus that combination, which is a better combination? How can you tell which one's a better combination? In other words, how do you know a double replacement reaction occurs? What's a driving force for double replacement reaction? Reactivity? Yeah, reactivity we can do. Reactivity. But how do you quantify reactivity? Tell me what the reactivity of HNO3 is. How do you quantify it? The strength of the acid, that's good. But the way we quantify it, it could be weak and still be more reactive. In terms of reactivity, weak or strong, it doesn't really matter because what we're doing is we're comparing it. We're comparing it to the products. And so when we're looking at this is called driving force. Driving force is which is more stable. I know this is a strong acid, but what if I gave you acetic acid? Is that very reactive? It's less reactive, but it could be still very reactive. That is, it depends on what you're reacting it with. So if I have magnesium metal, it doesn't really matter. I could use nitric acid to eat up the magnesium metal, or I could use acetic acid. Acetic acid works perfectly fine for eating up magnesium metal. And so it's a comparison. We're comparing things. And so when we look at driving force, and this is just for metathesis, this is not for all reactions. One of the biggest mistakes is that somebody will try to apply these rules to redox reactions. These rules don't work for redox reactions. Redox reactions play by a different set of rules. These rules work okay for acid-base reactions, certain types of acid-base reactions, not all. And so I'll just say driving force for metathesis. So in terms of reactivity, it doesn't have to be a strong acid, it just has to be a stronger acid. So let's say AB is a stronger acid, but AD is a weaker acid. And so if we're going from AB, a stronger acid, to AD, a weaker acid, that's a driving force. So stronger acid to weaker acid. Now, in terms of energetics, a strong acid is unstable, reactive, a stronger acid. A weaker acid is less reactive, more stable. And so here we're dropping down in energy. This is like what we call downhill in terms of process. And let's take a look at some examples of this here. The chart. So I did put the acid base and the redox chart on Canvas as well. And so let's see. Why this always pops up. So it's in the week 1 module here. So let's see what I can here. So anyway, what the favorable ion combinations are going to be combinations of H plus any anion D. So we're looking at H plus some anion D. D could be, we'll just call it negative X here. It could be -1, -2, -3. But what we want to see is that when H plus combines with D, it forms a weaker acid than with H plus and NO3 minus. So what are the anions that we look at for reactivity here? There we go. So when we're looking at it, what anions does H plus like? Well, H plus likes this one. This is called trichloroacetate ion. If H plus reacts with trichloroacetate, what does it form? It forms trichloroacetic acid. Trichloroacetic acid is borderline strong acid. It's these chlorines. Having 3 chlorines on here, making a trichloroacetic acid versus 3 hydrogens here. 3 hydrogens here makes it a lot less acidic. Like when we compare trichloroacetic acid to acetic acid, trichloroacetic acid is significantly stronger. Here's acetic acid. Is that trichloroacetic? Listen, it seems to be an error. No, there's no error here. That's correct. Here's acetic acid, and it's significantly stronger. Why do you think that is? Why do you think trichloroacetic acid is so much stronger than acetic acid?
Is chlorine a stronger base than?
Chlorine,
Chlorine's very reactive.
chlorine's not that reactive in trichloroacetic acid. It's not the chlorine that's reacting in trichloroacetic acid. It's the hydrogen. We're looking at the hydrogen's much more acidic.
The chlorines are playing with electrons farther away from the hydrogen.
Yes. Yeah. What was that effect called?
Electronegativity.
Well, it's because of the chlorine's high electronegativity, but what was the effect called? We talked about it yesterday. So this is an example. Inductive effect, exactly. So, as I was saying earlier, it takes time to build the neural connections. And so you look at the inductive effect example we gave I gave yesterday, which was, what was the inductive effect example I gave yesterday? Yeah, nitric versus nitrous acid. Nitric versus nitrous acid. The thing is, and this is going back to my my research on studying. My research on studying is you don't want to have to cram this the night before the test. You know, if you had read it last night, let's say, okay, that's the first time you see it, and maybe you forget it. But let's say by the time the exam comes along, which is a week actually, or the final exam comes along, you know, by the time the final exam comes along, how many times have you read, you know, nitric versus nitrous, and you see the inductive effect? And then you can start applying it to other things. You know, this is the exact same thing. We have these electronegative chlorines here sucking electron cloud density away. And it's going to be sucking electron cloud density away from the hydrogen here. Now, if we drew out the Lewis structure for this, we could see
And usually people do this, and they write out the inductive effect like this. We can have 3 chlorines here rather than 3 hydrogens. COOH is what we call the carboxyl group. This is this acid,
carboxylic acid, part of this. And so,
we can compare this with this. Now, if we have hydrogens, you know, carbon is more electronegative, just slightly more electronegative than hydrogen. So this carbon is much more rich in terms of electron cloud density. And so there are 2 ways, when I look at these two, there are 2 ways I look at the acidity of these two.
one way is the inductive effect. The inductive effect, we just draw the arrows.
So the chlorines are sucking electron cloud density away from this carbon. That's going to make carbon quite electron poor, which is going to help suck electron density from this carbon. But this carbon is also electron poor. But, you know, we're just comparing these two. So this one may go this way or may go the opposite way. And this oxygen is sucking electron cloud density, and which makes this carbon kind of poor here, which makes it suck more electron density away. And so even though this is backwards from what we've seen normally, it may not be. It's just a lot more even of a fight. You know, normally oxygen easily strips electron cloud density from carbon. But that's a normal carbon. This is not a normal carbon because look at this carbon, what it's attached to. Do you see that? What makes the bonding environment a lot different. This is the way when we look at structures, we start thinking about such things. Do we have much of an inductive effect here? Well, these bonds are fairly non-polar, but carbon is just a hair more. So I'll draw a tiny arrow towards carbon here, and a tiny arrow towards carbon. These are essentially non-polar covalent bonds here. This carbon, though, is going to, you know, when we compare the 2 carbons, these 2 carbons are different. Do you see that? When I look at these 2 carbons, I see a different carbon. And what's the difference? Well, this carbon is going to be a lot richer than this carbon. Why? Because this carbon has this oxygen sucking electron cloud density like this. Do you see that? And then we have this here. This kind of inductive effect going on here. So not really with the inductive effect, we just have a train of arrows going one way, sucking out to the terminal. In this case, it's only going to suck out to this terminal because these aren't here. That's option 1. Option 2 is you look at the oxidation states. When we look at the formal charge on all these atoms are the same, 0. What are the oxidation states on these? So let's compare the oxidation states of this carbon versus this carbon. What's the oxidation state of this carbon?
Sorry, which carbon again?
Well, in these 2 structures, these 2 carbons are the same. You see, they're the same because it's a CCOO. CCOO. You see, well, the bonding environment's the same. So these, I expect these to be the same. This is the carboxylic acid group. It's called a functional group in organic chemistry. Makes acids. Weak. These are all weak acids. Except this one. This was borderline strong. Trichloroacetic acid.
+1.
+1 on this carbon here.
I see where you can get a 1, but it's not plus 1. It's not plus 2 either, but it is plus. Plus 3. Plus 3. Because carbon loses these to chlorine, loses these to chlorine, but it's a tie here. Carbon versus carbon is going to be a tie, even though these two carbons aren't the same. So we split it. And that means carbon ends up with 1 electron. How many valence electrons does carbon have? 4, so it's lost 3, so it's going to be plus 3. That's how you get it. And so this is plus 3 here. How about this carbon here? Yes. This one has, because carbon wins in this case, even though it's slightly more electronegative, 2.5 versus 2.1, just slightly more electronegative. So, but it's going to win because winner takes all. We're assuming 100% ionic, even if it isn't. This is more closer to 100% covalent, but we do oxidation states to help us understand things like redox properties and sometimes acid-base properties as well. Primarily redox properties. And when we compare oxidation states, we're making the same base assumption for all of them. And so this is 2, 4, 6, and then half of this would be 7. It has 4 valence electrons. It's going to end up with 7, which means it has 3 extra valence electrons, which means minus 3. Do you see these two are totally different? This one is very electron poor. It's going to suck the electron cloud away, and that's going to make this one more positive, even though the oxidation state of this one's plus 1 and the oxidation state of this one's plus 1. But, that's the extreme, extreme. We're actually somewhere in the middle, or not in the middle, somewhere between the two extremes. But we need quantum mechanics to actually calculate it, but we don't do everything on a computer, do the calculations. It'd be too much work. Unless unless you had easy access.
What are the marks that you have on among the bonds for
This one?
the
Yeah, this is supposed to be a small dipole arrow pointed towards carbon, like that. And so I just tried to shrink it down. It's pretty poorly drawn, but. And so
24 carbon?
pointing towards carbon, because carbon's 2.5, hydrogen's 2.1 in terms of the Pauline's electronegativity scale. And therefore, the dipole should be pointed towards carbon. However, delta EM, the difference in electronegativity is 2.5 minus 2.1, which is 0.4. 0.4 is classified as nonpolar covalent. It's not 100% nonpolar covalent, though. There's a little tiny bit of polarity to the bond. And so this one's going to generate a much smaller delta plus. And these ones generate tiny, tiny negligible delta pluses. You would need a super base to pluck these hydrogens off. But super bases do exist, and so there's potential for plucking these hydrogens off. The easiest one to pluck off would be this one. And this one would be easier. If you're hydroxide, which one are you going to go for first? The easier one, right? And so this is going to be the stronger acid. Stronger acids are less stable, more reactive. And then we have weaker acids. Less stable. And so anyway, we're comparing. We're comparing hydrogen with nitrate versus hydrogen with trichloroacetate. And trichloroacetic acid is weaker, so we're dropping down in energy, which means we're gaining stability, less reactive. And so, as far as this, I don't want to do every trichloro. Where can I get trichloroacetate? Well, I could use the sodium salt, sodium trichloroacetate, potassium trichloroacetate, magnesium trichloroacetate, calcium trichloroacetate. Do you want to go through and list every single salt? So this is why a pattern like this only gets you so far, And so this is why I call it metathesis, because it's much easier to just look at the combinations of the ions regardless of the source of the ion, And so here, it doesn't matter, any salt that contains trichloroacetate will react with nitric acid. And then sulfate, any sulfate salt, sodium, any soluble, I should say soluble sulfate salt, because we need the sulfate to be free to react. If it's an insoluble salt, then the sulfate ion's locked in the lattice, crystal lattice. And you dealt with lattices before, ionic lattices, correct? Ionic lattice. Sulfate forms pretty strong ionic lattices. It's got -2. In fact, let's take a look, because when we do these things, we need to look at, well, let me finish this and then we'll look. We need to look at the solubility rules. I'm going to write the solubility rules over here. There are different sets of solubility rules. So what we need is sulfate. Most acetate salts are soluble. Acetate salts are they're -1 salts. Do you remember Coulomb's law? Coulomb's law, lattice energies. Do you remember the lattice energy? What makes a strong ionic lattice? Tell me characteristics of a strong ionic lattice. Well, strong ionic lattice has strong ionic bonds. What types of things make strong ionic bonds? So think in terms of Coulomb's law is very important. It says the force of attraction or the force of repulsion between two particles depends on the charge on particle A and the charge on particle B divided by the distance between the center of charges squared. That's Coulomb's law. And so the stronger the ionic bond force, what are we looking for in terms of Coulomb's law? Well, we want high charge or low charge? High charge. The higher the charge, the stronger the force of the ionic bond. In other words, the stronger the ionic bond. And what else do we need in a strong ionic bond? Bigger distance or smaller distance? Smaller distance. But in an ionic lattice, as you recall, the ions are actually touching one another. But what we look for is we look at the charge density, And so we could have a big ion, a -1 big ion versus a -1 tiny ion. Both of them are -1 charge, but what you have is in a tiny ion, that negative charge is concentrated in a small volume. In a big ion, the -1 is spread out over a large volume. And so which one's going to be more reactive? A small or a big -1 ion? A small one. Small one is going to be much more reactive. And how do we get a gauge of the size? We get a gauge of the size by the distance between the center of the ions. So if we have small ions, the distance is close between the centers. If we have big ions, then the distance spreads out further, even though they're both touching one another. And so the actual distance is 0 between the ions, but the distance between the centers changes depending on how big or how small it is. And so all the Coulomb's law says is the higher the charge and the smaller the ions, the stronger the lattice. And so usually +1 and -1, those are all soluble. Remember group 1 salts are all soluble? Right? Oh, well, group 1 are all +1. Ammonium salts are all soluble. Ammonium is a big +1, NH4 plus. Actually, let's not go to chlorides, bromides, iodides. We'll go to nitrates, chlorates, and acetates. Nitrates, chlorates, and nitrate, -1. Chlorate, -1. Acetate, -1. And they're big. So they're weak. Not that big of a force. So those are all soluble, right? There's more to it than just a Coulombic attraction. When we look at lattices, there could be some covalent bonding in there as well. Because we go on to chlorides, bromides, and iodides. Chlorides, bromides, and iodides are all soluble except for which Chlorides, bromides, and iodides are all soluble except for when paired with. No, zinc chloride, zinc bromide, zinc iodide are all soluble. It's not zinc. It's close. Close to zinc. Silver. But you think, hey, silver is a +1. But when you get to these heavy metals like silver, mercury, lead, there's much more covalent interaction in the bonding. It's not purely electrostatic ionic. It's electrostatic, like covalent. You know, covalent has a different type of electrical attraction. So these are the patterns we look at. And so here's some simple solubility rules.
Yeah. You might have had different ones, you know, but usually people in Chem 1B will have these memorized. In Chem 1A, I make the students memorize. In fact, in Chem 4, I make them memorize this.
What was the name of that over there?
This one, this equation?
Yeah. Okay. This equation is Coulomb's law. There's more. It's equal to. There's a constant here. All we need to know is what it's proportional to. This is the force of attraction or repulsion. It's an attraction if they're oppositely charged. It's a repulsion if they're the same charge, you know, both positive or both negative. And so, in other words, this is going to tell us this is one of the characteristic things that will tell us the strength of a bond, especially ionic bonds. When we look at bonding is, you know, when you look at the MO theory of bonding applied to lattices, we call that, we can take MO, what was MO theory again? Was that the full version of quantum mechanics or the light version of quantum mechanics? MO theory. That was the full version. So if we apply MO theory to lattices, we get something called band theory. And in band theory, you have things like, we have something called the band gap. And for metals, there's no band gap. And then for semiconductors, there's a very small band gap. And for insulators, there's a very big band gap. And so we can apply that to those. In fact, we're going to do that in Chem 1B. We're going to apply MO theory to solids, lattices, and we'll look at band theory for metals, semiconductors, and superconductors. They're different modes, mechanisms. So for example, you can just take a normal metal and get it to superconduct. And the way you get it to superconduct is you cool it down. You know, normally at room temperature, you have a lot of, you guys know the motion, molecular motion or atomic motion. We have 3 types of motion. What are the 3 types of motion for molecular or atomic? Atomic, I shouldn't say 3 types for atomic. But normally when we think of kinetic molecular theory, there's 3 types of motion that we categorize. The 3 types of motion. This is this is not Chem 1A, but repetition always helps to remember things. And so I'll just talk about the 3 types of motion now. One type of motion is translational motion. So you're going from this point in space to the other point in space, translational motion. And so we learned that, gases have translational motion and liquids have translational motion, but solids do not have translational motion. Right? Some solids do. There's something called superionic conductors. Superionic conductors are solids that have little tunnels through because of the crystal lattice. They have tunnels through it. And these tunnels that are in the lattice, ions can travel through these tunnels with very little resistance, making them superionic conductors. These superionic conductors are being looked at for solid-state batteries because a lot of batteries, the electrolytes that they use, which is an important component of the battery, are aqueous solutions or paste. Involve some water in there. Look at your lead acid battery, your car battery. The car battery weighs a lot. One, because it's got a lot of lead in there. Two, because it's filled with sulfuric acid, which is an electrolyte. There, sulfuric acid solution. However, for just a typical metal like this, you can make this superconduct. How can you make this superconduct? You can make this superconduct by cooling it down because, you know, in addition to translational motion, what types of motion are there? There's vibrational motion and one more, rotational motion. So we got translational, vibrational, rotational. In a solid like this, we only have vibrational motion. So the atoms are vibrating in this. What you need to do is you need to cool this down to something called the TC. The TC is the critical temperature. And the critical temperature is when the vibrations slow down enough that they don't interfere with electrons going through. And the electrons, when we apply band theory to this, you know, electrons are in one of the bands. The bands consist of these molecular orbitals that encompass the entire solid. And so it's freely mobile. It's kind of like the electron C model that you might have heard about, the electron C model of metals. Yeah. Where the electrons are like the ocean and the atoms, the nuclei are like the pier pilings. And so the electrons are mobile. Well, you know, you got these bands. But the problem is the pier pilings are stationary, they're fixed. But imagine the pier pilings vibrating around. That's going to interfere with the travel of the electrons or boats or whatever, you know, by there. And so if you could slow down the vibrational motion to the point, it doesn't have to completely stop, because if it completely stops, then you're out with temperature.
Absolute zero.
Absolute zero. So you just have to get it to the point where there's so little motion that the electrons can travel freely in the bands. And then that's it. Now, there are different mechanisms. That's for metals. All metals will superconduct at a certain temperature. But that temperature is so low, you know, that temperature is so low, it's too expensive to cryogenically cool it to that temperature. And so what people are after is they're after high temperature or high TC superconductors. So one of the big ones was the yttrium barium copper oxide. You know, yttrium barium copper oxide. Actually, when I was at UCLA, I was working a little bit on superconductors. And so I made some yttrium barium copper oxide. But the problem with yttrium barium copper oxide is it's a ceramic. It's very brittle. It's very brittle, and also the energy, you know, the number of amps you can throughput that. But that has a totally different mechanism. And so that mechanism was being explored. There's also, when I was at Santa Barbara, there's also a professor at Santa Barbara, Professor Woodle there in the physics. He's a chemist, but he works in the physics department at Santa Barbara. And he was working on organic polymers or organic, well, they didn't even have to be polymers, but organics. And there's a difference between inorganics and organics, right? Organics that superconduct electricity. So it'd be like you know, they're looking at plastics that might superconduct electricity. When I was at UCLA, just as a side thing, I was working with plastics that don't superconduct, but plastics that can conduct as well as copper. Copper is like the benchmark for conductivity. If you have conductivity equal to copper, that's excellent electrical conductivity. And so usually everybody compares it to, you know, the electrical conductivity or the resistance of copper metal. And so we were working on, or I was working with a group that was making plastics that conduct electricity as good as copper. And so it weighs a lot less than copper. But there was one major problem. And the major problem was that these were so unstable that the minute they get exposed to moisture in the air or oxygen in the air, they would decompose, you know. So if you had some of this superconducting plastic and you put it in air, then you'll see smoke and it's gone. No, not in the because vacuums eventually, it's a perfect vacuum is too difficult to get. And so even if you had a vacuum, there's a tiny bit of contaminating gas particles in there. And so what you do is you could store it under vacuum, but you would have to first fill it with a different atmosphere. So normal atmosphere that we'd fill it would be like with pure nitrogen. Pure nitrogen has a triple bond. Nitrogen's triple bond is about 1,000 kilojoules per mole to break, so it's a very strong bond. And so it's fairly inert. Nitrogen's a pseudo-inert gas or pseudo-mobile gas. So you could put nitrogen in there. But the other things is, you know, getting a good enough vacuum is very difficult and energy intensive. And so usually what we'll do is we'll just store it in a different atmosphere. That's much easier and much cheaper to do. So you put it under pure nitrogen or pure argon or pure helium. And so most of the time I used argon because argon is heavier than air. And so if a little bit of air contaminated my vessel, the air would be floating on the top of the argon, basically. And that way it would be, I'd have less of a risk of right. So a lot of people use helium, but helium, a lot of labs use helium. But helium is, no, I don't think anybody's using helium anymore because helium is very expensive, one, you know, and helium, you know, there's a fixed amount of helium. Well, I shouldn't say there's fixed because you can make some by like nuclear reactions, but you know, there's a limited amount of helium. And the people who use a lot of helium, I used to use lots of helium because I worked in NMR, nuclear magnetic resonance, and there we needed a superconducting magnet, and so we had a coil of wire in this magnet here. And how did we cool down the metal? I forgot what the metal was. How did we cool it down? We cooled it down with liquid helium. Liquid helium boils at 4 Kelvin. And so you cool down this. This is really cool because this magnet, you just plug it in once to get it started, this electromagnet. And then once it's going, you unplug it. And then it's just, the electrons just keep going and going and going because it's superconducting. And it doesn't stop. There's no resistance to stop it. The only bad thing is, and nobody wanted to do this because, you know, being part of an NMR group, you're responsible for maintaining the NMR too. So once a week, fill with liquid helium, but liquid helium is very expensive. And so there were two containers surrounding the magnet. One was the helium, and then around the helium we had liquid nitrogen. Liquid nitrogen is much cheaper, and just lots of liquid nitrogen. So every day we had to fill the liquid nitrogen up because it's just constantly boiling off. You know, liquid nitrogen, you just see this plume of nitrogen coming off the top. And then once a week had to refill the helium because if the helium level drops too low, then what happens is it quenches the magnet. That is, it stops superconducting. And then that's very expensive to get, you know, superconducting again. But anyway, this I got sidetracked. Was there a question I forgot to answer? No. No. So looking at the solubility rules, this is the pattern. You know, the pattern is, you know, low charge species, big species are mostly soluble. High charge species, small species are mostly insoluble. You know, that's kind of, you know, this is what we often do when we see a lot of data like this, and we write little annotations on the side, you know, describing it, what's happening there. You look at that, this is a jumble of stuff. So, as far as the solubility rules go, we have this. We look at the cation first. And the cation is group 1 and ammonium.
are all soluble. These are fairly big, you know. Where are the biggest atoms on the periodic table? On the left side or the right side? Left side, right? They're fairly big. The group 1, those are big. And they make big cations too. Although the cations are about half as big, you know, half the size. So if you have a sodium atom, sodium cation is about half the size, but still big, you know, compared to the ones on the right or in the middle. Group 1, ammonium, all soluble, and then what? Then we look at the anions. What anions do we look at? Nitrates, chlorates, acetates. There are two ways that acetate's commonly written. The general chemistry way, 2, 3, 2, 1 minus, you know, this is the way I memorize it, 2, 3, 2 minus, 2, 3, 2 minus. When you get to organic chemistry or something like that, then this is the way it's usually written. CH3COO minus. This is what we call a condensed structural formula. The condensed structural formula, I look at that and then I can just visualize the formula for this, you know. CH3COO, and then we lose that hydrogen and we end up with another lone pair there. It's minus, COO minus, that's acetate. This is acetic acid here. It doesn't matter which way you write it, you know. Acetic acid, HC2H3O2 or CH3COOH. COOH, this is not a peroxide bond. COO, you can't make this a peroxide. If you try to make this a peroxide bond, that is linking two oxygens together, it doesn't work. You're not going to get a structure that obeys the octet rule that has decent formal charges. You can try all different kinds of structures with a peroxide bond like this, and none of them look good. And then you go to something like this, it works. So nobody in organic chemistry mistakes this for peroxide. Nobody. But I'll tell you, in Chem 1A, Chem 4, Chem 1B, I still have students mistake this for peroxide. They try to draw peroxide here for some reason. It's not peroxide. Nitrates, chlorides, acetates are all soluble. And then we go on to chlorides, bromides, iodides. Chlorides, bromides, iodides are soluble, except when paired with silver ion. Silver ion, what's the charge on silver? +1. It's fixed charge. There's only one charge on silver, and it's +1. Please don't write silver with a +2 charge. There's no silver with a +2 charge. You know, even though +2 is pretty common in transition metals, not with silver. Lead has +2 and +4, right? Lead 2. Lead 4 is more molecular, more covalent. Lead 2 is more ionic, more ionic lattice. And mercury 1. Mercury 1 is Hg2, 2+. 2 mercuries. Each mercury has a +1 charge, so it's mercury 1. Mercury 2 is covalent. Mercury 2 forms molecular compounds. So mercury 2 chloride forms molecules. Mercury 1 chloride forms an ionic lattice. They're different. And this has to do with the bonding, you know. These are more ionic, whereas the higher charged ones are more covalent. Chlorides, bromides, iodides, and then we go on to sulfates. Sulfates are soluble. Now this is interesting because sulfate is -2. And so at -2, you expect it to be less soluble. But it turns out sulfates are, it's kind of a big ion though. It's a big -2 because you got 4 oxygens on there, you got the sulfur. So it's kind of a big ion, you know, tetrahedral, like a ball-shaped ion. These are soluble except when paired with silver is borderline. So silver I'm going to write it with an asterisk up here. It's borderline. It may or may not. So silver, and then but lead 2 for sure. Lead 2 and sulfate form a nice strong lattice, 2+, 2-. This stuff will precipitate. These ions like each other. So sulfate likes lead, for sure. And maybe silver, but not as much. Mercury 1, Mercury 2. Now Mercury 2 sulfate is more ionic, lattice rather than molecular. Mercury 2, and then calcium, which is a 2+, strontium, and barium. This is kind of weird, this one, because let's say I had iron 3 sulfate. Iron 3 is high charge, right? Iron 3 is high charge, and sulfate, you'd expect that to be insoluble. That is, you'd expect those ions to really like one another and precipitate, but they don't. And so there's more to it than just purely electrostatic arguments. It also depends on lattice structure, et cetera, et cetera. But, you know, at a crude level, yeah. So these ions like sulfate. So if I had sulfate, what are the chemical properties of sulfate? One of the chemical properties of sulfate is it likes silver, lead, mercury, calcium, strontium, barium ions. That's one of the chemical properties. And that chemical property is called metathesis. It doesn't matter the source, you know. You need some kind of source for that. Then we're going to go to hydroxides. Now, interestingly, oxygen is pretty small. You know, as you go across the period in the periodic table, what happens to the size of the atom? It's smaller and smaller and smaller. So oxygen is pretty small. Fluorine's pretty small. What's the smallest atom on the periodic table? Hydrogen. Close, but it's weird, but it's not hydrogen. It's helium. Helium is the smallest atom on the periodic table.
Smallest in terms of what?
Size. Not smallest in terms of mass. In terms of mass, you're right. Hydrogen would be the lightest, but helium is the smallest. Helium is the small. Why? It's got more stuff. Well, the reason is it has 2 protons, 2 electrons in the 1s orbital. 2 protons and 2 electrons in 1s. The electrons in the 1s orbital get pulled into the nucleus, like, you know, those tractor beams like in science fiction movies. Whereas hydrogen only has 1 proton and 1 electron in 1s. Well, 1 proton, this is a Coulomb's law. 1 proton, positive 1, 1 electron, negative 1. 2 protons, positive 2, electron, negative 1. Positive 2, stronger Coulombic attraction. Going to be smaller and more dense. Hydroxides are insoluble. And so these first ones were soluble. Now we're talking about mostly insoluble. So hydroxides are mostly insoluble, except for group 1 and ammonium and calcium, strontium, and barium hydroxide. Something that impacts chemical reactivity is how free the ions are to react. So sodium hydroxide, strong base or weak base? Sodium hydroxide, strong base or weak base? Strong base, right? Magnesium hydroxide, strong base or weak base? Weak. Calcium hydroxide, strong base or weak base? Weak. Strong. See, there are different ways you can remember this. You could just maybe memorize them all the hydroxides. Iron 3 hydroxide, strong base or weak base? Iron 2 hydroxide. Lead 2 hydroxide. Zinc hydroxide, cadmium hydroxide, manganese 2 hydroxide, manganese 3 hydroxide. You want to memorize all those individually? No, that would be a waste of time. So how could you figure out what the, I'll tell you what the strong bases are. The strong bases have lots of hydroxide, right, present in water. And to have lots of hydroxide present in water, You take some sodium hydroxide, group 1 hydroxide, dissolve it in water, you get lots of hydroxide. Right? Just like a strong acid has lots of hydronium. A strong base will have lots of hydroxide. And so what the strong bases are the soluble hydroxides. And so all the group 1 hydroxides are strong, ammonium hydroxide is strong, calcium, strontium, and barium are strong. All the other hydroxides are insoluble. The insoluble hydroxides are going to have the hydroxide ions locked in the lattice. Yeah, they can react, but they're going to be less reactive because they're locked in the solid. So something can attack the solid surface and get it to react, so it'll still be basic, but not nearly as basic. And so that would be like magnesium hydroxide. Magnesium is a lot smaller, right, than calcium. It goes like this: magnesium, calcium, strontium, barium ions. And so magnesium's small, therefore its hydroxide is insoluble compared to calcium, strontium, barium hydroxide, right? Beryllium would be even more. Beryllium, do you see beryllium there? Beryllium ions would be even smaller. Beryllium ions are tiny, tiny. Fortunately, we don't work too much with beryllium. Do you know why? Because did you know like magnesium has some good structural properties, like in engineering, like people like magnesium wheels or magnesium airplanes or magnesium. Why? Because magnesium is very light and it's pretty strong mechanically.
What are they bonding
Hmm?
to? What are they bonding to?
To itself, to make a framework like this. Aluminum is pretty light and strong, but magnesium is even lighter.
Pretty flammable.
Aluminum is pretty flammable too. All metals are flammable. All metals are flammable. It's just, if you have, it's like flour. Is flour flammable? Like cooking flour. You're baking a cake. Can you catch flour on fire? Yeah, and in fact, they have these things like, have you heard of grain explosions or bakery explosions? Bakery explosions it's not just flammable, it's explosive, and it's destroyed a lot of bakeries. But it has to be mixed with air in an aerosol, and then you could ignite it, it'll produce a huge flame or explosion, right? But it's like this. When I was in, I'll tell you, when I was in Boy Scouts, we used steel wool to start fires. When you go camping, you bring some steel wool. So we always brought steel wool. And you're thinking, steel wool doesn't catch on fire, does it? It does catch on fire, and we use that to start the fires. Sometimes wood was hard to catch on fire. But if we bought steel bars of steel, let's say, I found these bars of steel at the scrapyard, are those going to work very well? No, it has to do with surface area and contact. So what you want is a fine aerosol. And so if you look at a bottle of copper metal, I don't know, all powdered metals are marked flammable. So when somebody thinks of pennies, do you think, my penny's going to catch on fire? Nobody thinks their penny's going to catch on fire because it's in gold. It's going to be not very reactive. But if you look at copper metal, let's look at the powder, and let's look at the label on a bottle of copper metal, powdered metal. So you could buy this stuff. I use this stuff too. Let's see that. The warnings I usually see are even more. Some of them are marked even explosion hazard.
Oh, this is bronze. Okay.
Probably not as fun. Anyway, fire procedures. Finely divided copper burns in air and in extreme cases ignites spontaneously.
You don't even have to have ignition source. You know, if you get, this is what causes the bakery fires. The bakery fires and bakery explosions, you know, they got flour everywhere. You know, and then it gets close to a light fixture, and that's enough heat to ignite it and go. Yeah. Maybe I should show you some bakery or
Anyway, ignite spontaneously. Use extinguishing agents suitable for surrounding fires.
Well, if you have a metal fire, do not use carbon dioxide fire extinguishers. You do not use CO2 fire extinguishers on metal fires. Do you know why? Because metals are powerful reducing agents, and you don't need a strong, oxygen is a strong oxidizer. You don't even need a strong oxidizer to oxidize metals because metals are electron rich. And so you could use a weak oxidizer like CO2. CO2 is a weak oxidizer. Like this. So if you're using a CO2 fire extinguisher, that's like fanning the flames. That's like giving more oxygen to the flame, and it's going to burn even more intensely. Because CO2, why is CO2 an oxidizer? Oxidizer is electron poor. Well, I guess that's one way of looking at it, but there's another way. The other way is what makes a good oxidizer from yesterday. What makes a good oxidizer? Like fluorine's a great oxidizer. It's electron poor. So fluorine doesn't even have oxygen, but it's a powerful, in fact, it's the most powerful oxidizer on the chart because it's electron poor. It wants to be fluoride. Well, as we saw the other day, this is +4, which means the carbon's electron poor, making it an oxidizer. It's not a very good oxidizer. CO2, compare CO2 with chlorine. You know, we exhale CO2. Does it cause any oxidative damage? No. If I tried to burn paper in CO2, would it work? No, CO2 would put out that fire, right? Because paper is not that good or not that electron rich compared to metals. I probably could use a CO2, not like, well, I don't know, bulk metal. But let's see. Maybe bakery explodes. Oh, this is gas explosion. Grain silo, I can do that. Oh, maybe this one is fine. This has to be the right conditions. Let's see. 150 pounds of flour. I don't know if the audio works here. We're probably going to get copyright violation on YouTube. Well, they're creating an aerosol there, but there are lots of ways you can create an aerosol. That's very dangerous, you know, the mixture of flour with oxygen and air. I should, let me fast forward this. I don't know what we're doing there. Well, it looks like they used some kind of explosive to do that, but
I think they have a different
Yeah.
meaning for exploding.
All right, yeah.
Oh,
All right, there we go.
They exploded it to make it airborne.
Yeah, okay, that's it. Well, the grain silos is another classic example. There are lots of grain silo explosions that have leveled. Grain silo dust explosion. There. Grain mill mega explosion. This is it. So, yeah. So it's the same kind of concept as this. This is just flour here. And it's highly flammable, when it's in the right mixture with air. So let me give you an example of this. There, like if you go to the grocery store, you can buy this stuff. Have you ever heard of milk of magnesia? What is milk of magnesia made out of? Milk of magnesia. Let's see on Wikipedia or something. It's magnesium. That seems to make sense, but magnesium what? Yeah, here it is. Look at the generic name. If you look at the generic name, what is it? Magnesium hydroxide. Can you eat this stuff? Will it kill you? Do people eat this stuff? Uses. This medication is used for a short time to treat occasional constipation. It is a laxative. So people drink this stuff. And so they're drinking magnesium hydroxide. But let's say you ran out, let's say you had some milk magnesia in the medicine cabinet, you ran out. But you have some drain cleaner underneath the kitchen sink, and the drain cleaner is Red Devil Lye. Yeah, and so let's look at it. In fact, I was over at Ralph's, and they sell lye at Ralph's. Crystal lye. Or actually, they had a generic. It was just lye. It was Red Devil Lye. Actually, here it is. This is what they had at Ralph's when I was there. Or Red Crown Lye. Maybe they changed the name. Yeah. So, you know what lye is made out of? Sodium hydroxide. So let's say you ran out of magnesium hydroxide, but you remembered you have some sodium hydroxide underneath the sink to clear up the clogs in the sink. And then you go, well, I don't want to drive to the grocery store to pick up some more magnesia. I'm just going to drink the sodium hydroxide. Is that going to work? Why not?
right.
Yeah. It'll probably create a hole in your stomach lining, but yeah, then you don't have to deal. But anyway, no, you wouldn't use it. Why? Why is because it's marked as a poison? But what's the difference? Magnesium hydroxide, sodium hydroxide? What is the difference between magnesium hydroxide and sodium hydroxide? Because some people don't care. Just give me any hydroxide. That's the active ingredient is the hydroxide, right? And so magnesium hydroxide or sodium hydroxide, does it make any difference? It makes a huge difference. What's the difference between those two? Because both of those have hydroxide. In fact, magnesium hydroxide has 2 hydroxides per magnesium. And you might think, oh, sodium hydroxide only has 1 hydroxide per sodium. And so maybe magnesium hydroxide is even more basic than sodium hydroxide because 2 hydroxides versus 1 hydroxide. And so maybe sodium hydroxide is even more mild than magnesium hydroxide. Is that a good argument? No, it's a pretty bad argument because you know what? One of them's soluble and Yeah, and one of them was a strong base, the other one's not, right? It's not a strong base because, what time do we go till today? Okay, thanks. It, okay. So the situation is, it's because it makes, when you drink, if you haven't drank the stuff, it's a paste. It's awful. It's like this tacky, it's like, it's ground up solid and it's powdered and it's a powdered suspension. So, and that's good. And the reason it's good is because the hydroxides are locked up in the lattice, in the crystal lattice. The hydroxide ions aren't free to react easily. Whereas sodium hydroxide is very soluble. So if you were to eat solid sodium hydroxide, this is solid sodium hydroxide here, then the hydroxide is released immediately. And you're going to get high concentrations of hydroxide versus magnesium hydroxide, you're going to get low concentrations of hydroxide because it's locked in that kind of lattice. There's a strong ionic bonds. Well, since we're on this topic, this isn't normally something I show on Chem 1A, but since we're talking about solubility rules, let's take a look at this. CDC. For lead poisoning, there's a medication. There are two medications that they used to give for lead poisoning. And we're going to talk about this in chapter 24, which is coming right up. Because EDTA is ethylene diamine tetraacetate, which is what we call a complexing agent. And so EDTA complexes with lead, it kind of captures it, and then it kind of disables it, because if the lead is trapped in this EDTA complex, it's unable to react with your proteins, especially sulfur-containing proteins, or disrupt other things. And so there are two medications for lead poisoning, actually more, but these are the two main ones: calcium EDTA, or disodium calcium EDTA, and sodium EDTA, or trisodium EDTA, although there's only two here. Because we're looking at calcium EDTA versus sodium EDTA. Calcium is +2, sodium is +1. EDTA itself is a -4 ion. So those are two medications. So we have calcium EDTA versus sodium EDTA. Which one of those two medications do you think is more aggressive at capturing lead?
Sodium.
Sodium EDTA is more aggressive. Why? Yeah, it's more soluble and it's easier. The EDTA, which is the active ingredient, is easier to break free from sodium than it is from calcium, right? And so sodium, and in fact, EDTA captures all metal cations, not just lead, but it captures calcium, it captures whatever's available, it's going to capture. And so sodium EDTA is more aggressive, it's more for acute cases of lead poisoning. And so that the only agent recommended for intravenous chelation therapy for children is calcium EDTA, right? Because you shouldn't use very aggressive medications on children, right? Without, testing. And so here's some case reports. This is from the CDC in Texas, 2005. In February 2005, wow. That was how many years ago? A girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary BLL, blood lead level, of 47 micrograms per deciliter. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed the elevated BLL. A complete blood count and iron survey conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. Chelating agents are what EDTA is. Chelating agents are common in complexes. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral succimer, an agent primarily used for the treatment of lead poisoning. The medication order subsequently was corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35 p.m., she was administered 200 milligrams of oral Suxamar. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter. Normal value for pediatric patients is between 8.5 and 10.5 milligrams per deciliter. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 0.5 milligrams per deciliter. Despite repeated doses of calcium chloride, all attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. So when was she admitted? She was admitted.
So,
4 p.m. something. The next morning, can you believe that? This girl was given the drain cleaner. You know, this girl wasn't given the milk of magnesia. It was tragic. Tragic. Pennsylvania, 5-year-old boy, dead. Drain cleaner instead of the milk of magnesia. You know? But some people say, what's the difference? Hydroxide, magnesium hydroxide, sodium hydroxide, big deal. What's the difference? Sodium EDTA, calcium EDTA? It's EDTA. We just need the EDTA to capture the ions, right? So 2-year-old, this isn't, you know, there are lots, unfortunately. 53-year-old.
how was it so overlooked if it seems like something that?
Well, you know, if you look at it on the shelf and you see sodium EDTA and calcium EDTA and you don't see a skull and crossbones, you know, and you don't see drain cleaner, then it's easy, maybe. I don't know. For me, I would be very careful, you know, but for others, you know, with maybe not that much chemistry or not that much training, they might think, you know, differently. Because the way these are marked, they should change the way that they're labeled. You're right. It should be labeled.
You shouldn't be able to like make that, yeah, that's a weird mistake.
It's a weird mistake, but you know what the CDC recommended from this? They recommended getting rid of sodium EDTA from all hospitals to prevent this mistake in the future, because I think even with it marked, and I'm not sure what the marking was on there, because you would think it would be marked, you know, not for pediatric use or, you know, for adult use or for acute. You would think they would have clear enough labels.
Or that you'd have to get it from like the pharmacist.
Yeah, right. Who knows, but you know, the ultimate recommendation, CDC recommends that the hospital pharmacies evaluate the need to keep sodium EDTA and then get rid of it, basically. Just get rid of it.
Why would they be storing a drain cleaner next to a medical, like?
Well, I'm just exaggerating. I'm exaggerating the drain cleaner but you know, it's kind of the same thing, isn't it? Isn't this the same thing as sodium versus magnesium hydroxide? So this is just I mean, if you maybe somebody hid the calcium, you know, maybe the calcium wasn't visible and the sodium was the only thing there, so they just grabbed that. You know, I don't know the whole circumstances, but yeah, those things should be looked at, because, you know, I mean, a 2-year-old, come on, 2-year-old shouldn't have happened. Well, makes me wonder. I don't know what the total. This is an old report. There are, to my understanding, there are quite a few of these cases. Okay, So this hydroxide, and then we're going to talk about the next anion, which is sulfide. Sulfides are insoluble, except group 1, group 2, and actually that's it, just group 1 and group 2. I forgot to talk about the group 2 beryllium. Did I finish what I was talking about beryllium? Beryllium was used in aerospace a lot. And so I think over here with all the aerospace companies located in the South Bay, there are a lot of machinists machining beryllium because beryllium is beryllium's actually the lightest metal that's structural. And there are lighter metals like lithium, but lithium is so soft you can bend it with your fingers, although you better wear gloves because you don't want to touch the stuff. Sodium is very soft. You can cut it with a butter knife, shape it in different shapes. But beryllium is pretty rigid. It's got some mechanical strength to it. And so they were using beryllium in the aerospace industry because it was very promising as a very lightweight material for the structure of the planes. But the problem was all the machinists ended up dying. Not immediately, but they all ended up having the same disease and ended up dying. And the reason is beryllium is very small and very reactive. And so if you need calcium and magnesium in your body, you don't want any beryllium. But what happens is beryllium will knock away the calcium, knock away the magnesium, and react preferentially with whatever. And so it disrupts the normal life. So beryllium we don't use at all. It's very toxic. And you could read about it. There's lots of stuff on beryllium online. I had a friend who bought some. Well, I have a friend that works at JPL, working on batteries, and he ended up getting some surplus equipment. Beryllium is also very good for X-ray windows. You know why beryllium's good for X-ray windows? What works good for X-ray shields? Lead. Do you know why lead works well as X-ray shield? It absorbs X-rays really well because why does lead absorb X-rays really well? Well, it's related to density, but when light is absorbed by matter, what does that light typically do? It could reflect, but let's say it absorbs. We want it to absorb. We don't want the X-rays to bounce out. If you go to the dentist, they'll put a lead apron on you. And they want it to absorb the X-rays. And when you go back, when light is absorbed, what did Bohr say about light being absorbed by the atom? What does the light do when it gets absorbed by atoms?
Doesn't it raise the energy level?
Right, it excites electrons, right? And what does lead have? Lead has 82 electrons, right? And so if you want something to absorb a lot of radiation, you want a lot of electrons, like lead. Well, there's things with more electrons than lead, right? Like what? Well, bismuth. Bismuth is not that easy of a metal to work with, but polonium does. Polonium has more electrons, 84 electrons, but what's the problem with polonium? It's radioactive. Actinium, radon's not a metal, but we can go to the heavier metals than that, and then they become either very rare or radioactive. Lead is cheap, it's plentiful, so lead is used as an absorber for X-rays. But if you want a window for X-rays, then you want things with the fewest number of electrons. And so beryllium is a structural material with very few electrons. So in the high vacuum stuff that my friend got was high vacuum stuff. And this high vacuum stuff is like a submarine. So the beryllium was used as a window into the submarine. And in that window, they shot X-rays to measure things in here. So he ran out of space. at his house. And so he asked me if he could borrow some space to store some high vacuum equipment. And so I started talking to him about the high vacuum equipment. And a lot of it had beryllium windows. And he said, oh, it's no big deal. I mean, it's beryllium. It's not, you're not machining it. You're not creating dust. You're not inhaling it. And so he thought it was no big deal. But I thought, I don't want it, just maybe find some other place for it. And so size and charge, are important. We're always thinking about size and charge, and these kinds of things, Coulomb's law, interactions like this, solubility rules, etc. So sulfides, oxides aren't on this list, because after sulfides, you think, okay, what about the oxides? Well, what would you think oxides would be? Would oxides be less soluble, that is, have fewer exceptions, or more soluble than sulfides in general? Oxides versus sulfides, which one would you expect to have more soluble, that is, more soluble compounds? Oxides should have the greater number of soluble compounds? Why? It's smaller, but if it's smaller, what does Coulomb's law tell you? If it's smaller, then it should be stronger. If it's stronger, is it harder to break apart and get in water, or easier to break apart and get in water? Harder. So we expect oxides to be even less soluble than sulfides. That's purely Coulombic. But there's something else about sulfides. Sulfides have more covalent interaction with and so it's tricky, but in terms of oxides, group 2 oxides are insoluble. Like, think about magnesium oxide. It's not very soluble. It'll react with water, but it's not very soluble in itself because of that. You expect. But the sulfide is soluble. But after sulfides, then we go to hydroxide sulfides, then we go to carbonates, chromates, and phosphates. These are fairly high charge species here, and these are insoluble. Insoluble unless they're paired with a very low charge species, except for group 1 and ammonium. All right, so this is going to give us keys to what ions like each other. So if I have iron 3 likes phosphate, chromate, and carbonate. That's going to form a precipitate. I can pick any cation, and any cation will like these except for which ones? Which cations would be unreactive with these? Group 1. So sodium ions? No. Potassium ions? No. Ammonium? No. No reaction. They aren't going to be attractive to each other. But every other cation will be, and will react with these. And so that's metathesis. We don't have to go one by one CD and check every CD. We just look at the favorable ion combinations, and these are the favorable ion combinations. The favorable ion combinations make a precipitate. Precipitates form strong lattices. Precipitates with strong lattices have strong bonds. And that's what we're looking for there. Okay, well, anyway, I'm now behind a little bit, but it's all right, because this is important for understanding. We're going to be looking at a lot of chemical reactions this semester, so